Let's start to consider standard deviations of samples. And again, I'll always indicate whether it's a sample or a population. Now, the problem with standard deviations among samples is they're presumed to be biased. And what does that mean? A sample statistic, like the standard deviation, is presumed to be biased if on average it consistently overestimates or underestimates the corresponding population parameter. So, as figure 4.4 says, the population of adult heights forms a normal distribution. If you select a sample, you're most likely to obtain individuals who are near average in height, and as a result, the variability of the scores in the sample is smaller. So we assume that the variability, the standard deviation and the variance, are smaller in a sample than they are in the population, and we systematically adjust for that. And here are the formulas. You'll notice that the definitional and computational formulas for the sum of squares are precisely the same, other than substituting capital M for mu and lowercase n for the capital N in the computational formula. That's it. So those two are precisely the same. Where we part company with the population is in the variance. We're now substituting lowercase s for lowercase sigma, and also now dividing by n minus 1. And why is that in the variance? That over the fullness of time, if we divide n minus 1, it has the property of inflating the variance. And over the fullness of all the samples that could possibly be taken from a population, if we add or take their average variance, it would be precisely the same of the population variance if we divide by n minus 1 every time. What's the rationale for dividing by n minus 1? Well, think of it this way. What's bigger, 1/3 or 1/2? Would you rather have 1/3 of a pizza or 1/2? Half is bigger, right? And by the same token, if we're dividing by n minus 1 every time, we're systematically inflating that sample variance, and the average of all sample variances using n minus 1 will equal the population variance. That's the reason. I don't press too hard on this. Every textbook gives literally like one paragraph or maybe two paragraphs on why we divide by n minus 1. But I do want you to just remember that that is the difference in the formulas. We have that one real difference besides the notation differences above. And then the standard deviation process is the same. We're just going to take the square root of the variance. So again, the reason we do that is because we assume that the sample standard deviation will underestimate the population. Okay, so the sample variance is represented by the symbol s squared, lowercase s, and that equals the mean squared distance from the mean. It's obtained by dividing the sum of squares by n minus 1. That's the key difference. And the standard deviation is just the square root of that sample variance. Fairly direct idea. Let's take a problem. So I've got these numbers and I'll faithfully list them in red. That's important. So here's 8, 6, 3, and -1. The sum of all of those numbers is 16. And I'm going to go ahead and undergo the computational formula. The sum of all those values squared, as you can see, 64, 36, 9, and 1. And again, squaring a negative is always a positive, 110. Sigma x squared is, of course, 16 squared, 256. And I can easily plug that into the formula. 110 minus 256 over 4, 110 minus 64, 46. Now, it should be said that if that sum of squares formula ever yields a negative, then a mistake has been made. The sum of squares could be 0 if the numbers were all the same, but there is no circumstance under which it could be negative. Here are the same numbers, since it has a nice rounded mean of 4, whatever that is, 16 over 4 is 4. Can I do it the other way? Sure. This is the definitional formula. So I subtract 4 from each number. 8 minus 4 is 4. 6 minus 4 is 2, etc. Get the sum of all those subtractions, get 0, and then square them all and get 46, just as we got before. How about them apples? So this really betrays the sum of the square deviations from the mean. And of course, I'll just undergo the formula now. Here's my variance. That 46 that we obtained both ways, don't have to do it both ways, but just wanted to illustrate that, divided by n minus 1. 4 minus 1 is 3. 15.33, take the square root of that, and get my standard deviation of 3.92. So a fairly direct idea. This literally what we're doing is I have to tell you that it's a sample. I could undergo it either way, given that it's a rounded mean. And strictly speaking, you could always undergo it either way if you want to deal with lots of decimals. It yields the same sum of squares. I could easily compute the variance by dividing by n minus 1 and then take its square root. And I'm always pretty, I guess you could say, direct about letting it be known that it's a sample by coloring things brightly in red. I'll come back and we'll talk about this idea of biasing again. Just mention it one more time.